discussed about processes, and this is chapter 4, which is about threads. So you already know what is a process and what does a process do. Okay, what are the activities for a process? We studied about process states, how a process transitions between different states. Now we are going to have another concept, threads, which is quite similar to a process because it is related to a process. So in this chapter, we will the objectives of this chapter are to introduce the notion of a thread. Okay, now this is a fundamental unit of CPU utilization that forms the basis of multi-threaded computer system. So we will see what is a multi-threaded computer system. Then briefly we will discuss the APIs for Pthreads, Windows, and maybe Java thread libraries. Okay, and briefly we will describe the support of operating system for threads in Windows and Linux. Now the motivation for this thread topic, the concept of thread, is that normally most of the modern applications, they are multi-threaded. Multi-threaded means more than one thread. If you remember from chapter 1, we discussed that a process can have one thread or multiple threads. Okay, and in such a way, because each application can have one or more processes, so each process can have one or more threads, which means that a thread is a part of a process, or a process consists of one or more threads. Now why do we need threads? Because an application can have more than one task, and what we can do is that we can divide the task of that application or that process into different threads. So each thread will be doing a different task. For example, let's say here is an example of Word, Microsoft Word. So Microsoft Word may have a thread for updating the display. So if you write something, so it will update the screen. Let's say I press some key, so it will show the output of the key press on the screen. Any character, any word, it should update the display. Fetch the data, it depends. Maybe it is getting data from the hard disk to compare with the data on the screen, or maybe you are opening a file, or maybe you are downloading a file from the internet. So that's a different task, and that can be done by a different thread. Spell checking, so as you write, Microsoft Word is checking for spell and grammar, and then if there is anything wrong with spelling or grammar, then it turns that, for example, red, it underlines that as red or green, okay, or maybe blue, depending upon what type of spell checking. Similarly, there can be the task of answering a network request. There is something from the network, okay, in some applications, for example Google Chrome or chat application, there is a chat which comes, so you have to display the update the display to include the new chat which comes from the network. So I can summarize that any single application can be divided into many tasks which are being done at the same time, and that's why we use threads, because each thread, it will do something related to that task. Okay, now another important thing over here is that when you create a process, so it is a heavyweight task, which means that it will take time, because process, it has a PCB, it loads into memory, the PCB must be filled with the information and some other things done by the operating system for the process. So process creation is heavyweight, it takes time, and if we are going to create a thread instead of a process, then that is simpler. It takes less time, okay, less resources. And yet another benefit of, or the motivation for using threads, is that threads, they can simplify the code and they can increase the efficiency. Simplify code because you can write the code of each task in a different class or a different function and use threads to run that class or that function. So that will be a different code, and your main code will not be affected. If you are going to change anything in the thread, you are going to change specific classes or specific files only, not the rest of the system. Similarly, the threads may increase efficiency of the application, efficiency of writing the code, okay, efficiency of execution the application, because if there is one process, it will be running on one CPU. But if a process has two threads or many threads, each thread can be executed on a different CPU, which means that a process can do its task in parallel. Okay, so at the same time you can check for spelling, and at the same time you can type and the system will be updated, and at the same time the system can change or create new pages, etc. For example, this was about the example of word processor. If you take the example of a browser, then you see that the browser is downloading something from the internet, okay, and at the same time you are clicking on the web page, so it is sending some data to the web server, and also locally on the browser it is doing some processing. For example, when you click on some button, it is going to do something locally according to the button click. Final point about multi-threaded is that the kernels, they are generally multi-threaded. So what is the kernel of operating system? Can anyone tell me? Let me answer like this, that the kernel is the main part of an operating system, which contains most of the functionality of an operating system. So for example, loading a process, okay, deleting a process, accepting commands from user, sending something to the screen, getting something from the keyboard, all these are the things which an operating system does for you. The basic input output, reading something from the hard disk, sending something to the hard disk, and all those functionalities normally that you see, which are provided to the user applications or any other applications, they are provided by the kernel. So kernel has the core functionality of the operating system. Okay. Now here is a diagram which shows two processes. One is a single threaded process and another one is a multi-threaded process. Now this thing which seems like a worm or a snake, okay, this is just an example which shows you a thread actually. Okay, so this is just a symbol for a thread. So here this process, it has only one thread, and the other process on the right side, it has three threads. Okay, so this is multi-threaded application, this is single threaded, and the important thing to see here is that the code, the data and the files of the process, so this is main process and it has threads. This main process code, data and files, they are shared by all the threads. So each of these threads, they can use the same code, okay, or they can use the same data, or any files which are opened by the process, they can be used by any of these threads. But each thread has its own set of registers and each thread has its own stack. Now you remember, why do we talk about data register stack? Because from chapter 2 we saw there that a process has four parts. One was the code, one was the data, one was stack, and another one was heap. Okay, heap was the memory. So heap is actually common to all of these, but the stack, each thread has its own stack and each thread has its own registers. Why? Because each thread works in its own way, so it may be calling a different function, it is having a different set of variables. Okay, it is executing in a different part of the program, so it has its own stack. Similarly, because it is executing differently, it has its own registers. So this thread may be executing some other part of this code, this is executing some other part, which means that each of the thread has different value for the program counter or different values in the register. You understand? Now, what are the benefits of using threads? If we don't have multi-threads, we only have one thread in an application, what will happen? And if you consider another application which has multiple threads, so what are the advantages or benefits of having an application with many threads? Now, the benefits are that as you increase the number of threads, okay, to a certain number, then the responsiveness of the application is improved. Okay, what is responsiveness? That if you interact with the application, you click on some button, you enter something, it will do that task for you. Okay, so how is it increased? How the responsiveness is improved? Because each thread is doing a different task. So for example, if a browser is downloading some file, that is done by a different thread, and the thread which you use for updating the screen, it is a different thread. It has nothing to do with the downloading of the file, which means that it is not busy. If there was only one thread, then the thread will be busy in downloading the file, and if you do anything, the thread will not be able to respond to you, and it will not be a responsive application. So this is especially important for user interfaces, because if you keep the user interface busy or the application is busy, then the user interface may not be able to respond to your clicks. Resource sharing is also one of the benefits of threads, because as I showed you in the previous diagram, threads, they share the resources of process, okay, and they can do different tasks, but still if one thread is producing some resource or changing some resource, the other thread can access that directly. Now compare this with the last chapter when we studied about inter-process communication. So in inter-process communication, we studied about two methods, shared memory and message passing, and those two were between processes. Okay, they normally are on the same computer. In one computer, the processes, they share memory or they pass messages with one another. So in that case, it takes time, because normally the kernel is involved to transfer the data or to map between the memory of two different processes as a shared memory. However, this is very beneficial in threads, because the operating system is not involved directly, the kernel is not involved, the threads can access the areas which are shared in the same process. There is also benefit in terms of economy, which means they are cheaper. To create a thread, it's cheaper in terms of resources, in terms of time, as compared to a process. Also, if you do context switching of threads, then that has lower overhead, okay, as compared to context switching of process. Thread switching is quickly and involves less time and less resources. Finally, with threads, you can have scalability, which means that you can run threads in parallel on different processors of the computer. So your job will be faster, okay, and it will be scalable, which means that as you increase the number of multiprocessor and as you increase the number of threads, it will be more beneficial. So these are some of the benefits of using multi-thread mechanism. Now another term that we study is multicore or multiprocessor systems, okay, because there are many processors and there are many cores, let's say, in a system. So we have challenges such as how do we divide activities, then how do we have balance of division of things in an application, okay, how do we split the data if you have multiple threads, they are working together. So this creates a challenge that you divide the data such that there is no dependence between data of one thread on the data of another thread. This is data dependency section. Similarly, testing and debugging of multi-threaded application, this is not easy. Many threads are working at the same time, and if there is an error in the program, you are not clear which thread is causing that, so you have to debug it in a different way. Then you debug a single threaded application. So this happens because of the parallelism. Now the two terms, one term is parallelism and the other one is concurrency. Parallelism means that two or more tasks can be done at the same time. How? Because you have two or more CPUs. So if you have two CPUs, then each CPU can do some work and they are working at the same time. This is called simultaneously. But concurrency is not necessarily parallelism. It may be possible that you are executing a task actually one by one, but they are switching so frequently, so quickly, that for a user it seems like the user there are more than one task which are executed at the same time. So even on a single processor or a single core, the scheduler, it provides concurrency. So in the previous chapter we discussed about context switching. So actually that is what is concurrency about, that you execute more than one processors at the same time. So types of parallelism we see normally when we want to parallelize our code, which means that things can be executed on more than one processor at the same time. Then one type of parallelism is data parallelism, okay, and the other one is task parallelism. Data parallelism means that we distribute the data, okay, so we have data, we divide it into subsets, okay, and then these subsets, they are actually assigned to different processors. Okay, so one processor, one part of memory, it is working on one part of data, and another processor may be working on another part of the data. Similarly, task parallelism, it means that the task or the thread, you divide it on the CPU such that each one is working independently and working at the same time, so that they can be work as parallel. Okay. How do we explain this notion of concurrency and parallelism? You can see this diagram. Okay. So one diagram shows the concurrent execution. This is only single core, but they are at the 4 tasks. They are executing concurrently. And the other one, the bottom diagram, it shows parallelism on multi-core system. So you have 2 cores and your applications, they are executing in parallel. Now if you compare the time, let's say you have 4 tasks, okay, they are executed in one followed by the another in a single core. So you can see it will take, let's say, 10 seconds. If each one, this slot takes 1 second, so you have 9 seconds, okay. But if you have multiple cores, then T1 and T2, they can be executed together. So this way the total time taken will be about 5 seconds, for example. So this is almost half of the time is reduced by the multi-core system, because you are executing more than one thread at the same time. One important concept of the threads is about user threads and kernel threads. Okay, so a thread can be executing in the user mode for user applications. Okay, we studied, if you remember, we studied 2 modes. One was kernel mode, one was the user mode. Okay, but that concept is different, because the mode, each mode would be responsible for different type of protection. So if something is run in the kernel mode, it means that it was actually secure, it was protected by the kernel, okay, and normal application cannot be executed in the kernel modes. However, user application, when they execute in the user modes, they can do certain things, okay, and in kernel mode they are not allowed to do those things. The difference between kernel mode and the user mode is in the basis of processor, hardware, okay. So hardware will allow the execution of different types of instruction in kernel mode, but some instructions will not be allowed when the CPU or the hardware is in user mode, okay. Now here we are talking about user threads and kernel threads. These threads, they are at the operating system level, okay, not at the hardware level, but at the software level inside the operating system. Now we have either user level threads library, okay, which manages the user threads, okay, and normally the famous ones are the POSIX Pthreads library, or the Windows threads library, or the third one is the Java threads. If you remember, we studied about API, okay, when we discussed the system calls. When we discussed system calls, we said that the system calls, they are for operating system. But sometimes you have different programming languages for the same operating system. Like in Windows, you can write programs in Java, C, C++, .NET, etc. Okay? So because of different programming languages, what you have that each language has an API, application programming interface, which translates your programming calls, okay, or your library calls into the lower system level calls. Same is here, that we have libraries which are for dealing threads. So POSIX Pthreads are mainly used in Unix and Linux threads, okay. Windows threads is the library or the API which is provided by the Windows programming languages, okay, Visual Basic and .NET, C#, etc. They have different threads libraries. And Java threads are actually the threads which are provided by Java programming language, okay. And when you program Java, you will use Java threads, but behind the scenes they will be using the threads of Windows, okay, when you are using Windows, or the threads of POSIX when you are using the Unix library system, Unix operating system. So user threads are those which are managed by the user or the programmer, okay. By user I mean a programmer who writes a program. The second type of threads, they are the kernel threads, okay. And the kernel threads, as it is written here, they are supported by the kernel, so they are managed by the kernel, okay. And all the operating system, they have support for kernel threads. For example, Windows, Solaris, Linux, Unix, Mac OS X, etc. Why are kernel threads important? Because this is how the kernel works. At the same time, there may be several dozens or maybe hundreds of threads of kernels which are representing different tasks for the operating system. For example, many threads of the kernel, they may be reading from the hard disk, or downloading something from the internet, or accepting keyboard input, etc. Okay, so these are the kernel related threads. Now the user threads, normally they will have some concern with the kernel threads, or they will communicate with the kernel threads, and we are going to study this in the next slides. So if there is some user thread and it is interacting with the kernel thread, it needs something from the kernel thread, okay, using a system call. So how do they interact? There are three types, three possibilities: many-to-one, one-to-one, and many-to-many. What does that mean? So on one side we have kernel threads, on the other side we have user threads. So this is the example of the first type of multi-threading support, okay, many-to-one. What you see here is that you can have many user threads which are connected or which communicate with only one kernel thread. Okay, what does that mean? It means that these different threads, if they need something, they will be using only one kernel thread to get their job done. Okay, so the problem in this case can be that if one thread it blocks with the kernel, okay, the other threads, they will not be able to communicate with that thread of the kernel. Okay, they will be blocked. So there is the problem that you cannot run multiple threads in parallel, or you cannot run on multi-core system, because at any time only one may be in the kernel. So that's many to one thing. Now very few systems they use this model. Okay, for example, Solaris and the GNU portable threads, they use this many to one model. I repeat, many threads, okay, they can communicate with only one kernel thread. The other type of model, the other type of this threading approach is one-to-one, which means that for each thread of the user, you have one kernel thread. So if user threads, there are many user threads in the application, there will be many kernel threads for the application. Okay, here whenever you create a user level thread, so automatically a kernel level thread is created for that. Okay, it has more concurrency as compared to many to one. In many to one, only one kernel thread can be executed at a single time, so the concurrency was limited. Here, because each user thread has a different kernel thread, so multiple threads can be executed at the same time on multiple cores. So sometimes you reduce the number of threads per process, because you don't want to allow a process to create too many threads. This will consume memory and this will slow down your process, so you have some type of restriction on the number of threads in one application. So Windows, Linux and some other operating systems, they use one-to-one. Remember this thing, huh? Windows and Linux, they use one-to-one. Now many-to-many model, you have many user level threads, and each of them, they can take any of the kernel threads. So this is many-to-many. Okay, so it allows different threads, number of user level threads, to different number of kernel level threads. In this way, the operating system can create a different number of threads before. Okay, let's say 10 or 20 kernel level threads can be created by the operating system, and any thread, user level thread, who wants to use a kernel level thread, it can just communicate with any of the available threads from the kernel. Okay, so Windows with the thread fiber package, it uses this many-to-many model. Okay, similarly, there is a two-level model. What do you see here? Can anyone explain to me what is here in the two-level model? So it is actually many-to-many, just we did before, but in simple many-to-many in one-level model, if I give you this example thread, so maybe it uses this thread one time and the next time it uses this mapping. Okay, so in many-to-many, these lines can be any of this. In two-level model, if you use this user level thread for this kernel, then it means all the times it will be using this combination, only this path, and it's not possible that this thread it will use the other kernel thread. Okay, so this is two-level model in which there is the possibility of many-to-many, but once you assign a user level thread to one kernel, that this relationship is created and they will be using like this almost all the time. Okay, yes, so we talk today, let's try to finish this chapter. Okay, so let's talk about the thread libraries. What is a thread library? Once again, I repeat that in chapter 1 or chapter 2 we discussed about application programming interface, okay, which actually provides a set of functions or some libraries to deal with the low level details of the operating system. For example, system calls in one operating system, it can have different APIs in different languages. Similarly, thread library is actually an API for creating and managing threads for different programming languages. Okay. Now there are two types of possible implementation for thread libraries. One implementation of thread library is possible to be entirely in the user space, which means, and you remember about the user space and the kernel space. User space means it has the same authority or privileges just like the user application. Okay, and the other one is to implement it as a kernel level library which is supported by the operating system. Now what is good and bad in these two? If you have user space implementation of this thread library, the good thing is that it is faster because you don't have to change the mode from user to kernel, etc. Most of the things can be done in the same user level. But on the other hand, it has the problem that it may not have access to lower level functionality, and it may need help from the kernel, which might be restricting or which might not be that much flexible. So there is a compromise of having implementation in either user space or in the kernel space, which with some provision from the operating system. This topic is not that important because this is related to implementation of thread libraries, so we are not going into the detail, but let's discuss threads types, because in some previous slide I discussed that we have Pthreads for Unix based systems, we have Windows threads, and also we have Java threads. Okay, so Pthreads is first of these types. This is possible that the Pthreads can be provided as user level or kernel level, and there is an API for creating and synchronizing threads in Pthreads. This is actually a standard. Okay, and this is a specification, not implementation. It means that how you implement it depends. So they tell you that these should be the function, this is how they should work, this is how you should create, this is how you should delete, but actually they don't give you the implementation. So anyone who is going to implement Pthreads, they have to follow this standard. Okay, now the API specifies behavior of the thread library. Okay, and how do you implement the behavior is dependent on the development of the actual library. Okay, Pthreads, that's why it's very famous, because it's a very good specification. It is accepted by many people and many organizations and many operating systems, so it's quite popular, and actually the interface is very good and it supports much functionality to complete all the things related to threads, whether creation, deletion, synchronization, message passing, etc. Okay, so Pthreads is common in Unix based operating systems, which includes Solaris, Linux and Mac OS operating system. Okay, so that's a brief introduction of Pthreads. The next thing is about Java threads. Okay, Java threads, they are managed by Java Virtual Machine. Okay, so Java Virtual Machine is used alongside the operating system. Java Virtual Machine runs as an application inside the operating system, and it manages the threads in terms of Java threads. Okay, and they are typically implemented using the thread model provided by the underlying operating system, which means if you use Java in Windows, then the JVM of Windows it will be using the Windows thread library. If you use JVM on Linux operating system, then they will be using the POSIX threads library, and similarly for Macintosh they will be also using POSIX, because both Macintosh is using Pthreads. Now Java threads can be created by using this runnable interface, and there is a method run. So when you call a method run by a thread, it will create a new thread and it will be running independently from the main process. So the number of threads you create, each one will be using the run method, and then the program will start running a new thread. Okay, if you have time, you should search Java threads, okay, in search engine, and you can have short programs of a few lines to understand how threads work. In general, threads is a very important concept in programming, in advanced programming, because your program, as I explained in the beginning of this chapter, it can be doing many tasks at the same time. So it's better that these tasks are done differently by different threads. So one way of doing this is to use the runnable interface. The other one is actually extending the thread class. Both of these, they are ways of implementing threads in Java. Okay. So operating system examples are Windows threads and Linux threads. Okay. The code examples they are giving in the book, we are not going into the detail, but just trying to understand how threads work. Okay, so first we take the example of Windows threads. Now in Windows, we have Windows API, which is working until this Windows 7. Then we have Windows 8 and 10. They have slightly different things. They have different architecture. Okay, the programming model, they have changed. There are new things. Okay, so it might not be the same thing as Windows before, but still the basic things you need to understand is that in Windows we have the one-to-one mapping between the user level threads and the kernel level threads. Now each thread has a thread ID, okay, which identifies it uniquely in the operating system. Each thread has a register set which represents the state of the processor, what are the values now inside the processor. And there are different user stacks and kernel stack. Okay, so when the thread runs in the user mode, it has user stack, and when it runs in the kernel mode, it has kernel stacks. Okay, then there is the support for runtime by the runtime library for private data storage. Okay, and then there is the concept of dynamic linked libraries. Dynamic linked libraries are actually those libraries which are there in the Windows operating system, which are already available, and when you install a new program, it needs some functionality, so it will use the dynamic linked library of the operating system to get that thing. An example of a simple library is the IOStream library in C++ or the stdio library in C. Now these libraries, they contain the basic input-output function for disk or screens or keyboard. Okay, so these libraries, they are part of the C library, they are available to you, and the users, they can use those libraries to have some input-output operations. Similarly, in Windows, you have DLL file concept. Let's say you want to print something, so you don't need to write the code for printing everything or to send the data to the printer or to see the data from the printer in your code. Rather, you will use the printing related DLL to load the information and then communicate using functions from that DLL with the printer. Okay. Now, as we know before from the context of a process, we also have a context of a thread. Now, what is the context of a thread? So it contains the set of registers, their values, okay, then the stacks for each of the thread, and each thread has a private storage area. Okay, these things, they comprise the context of the thread. Now the context of thread and the context of the process, they become different because process has more than one thread. Okay, and the process, it has its own data section and code section, and which are shared by each of the threads. But the threads, they are at smaller level, while they have all the threads, they have same code. So that's why the code is not part of the context of the thread. But because each of the thread, it is running different instructions, it is running different functions with different variables, so it needs its own register set, its own stacks, okay, and its own private storage area where it stores the results of the calculations, etc. In Windows threads, when you program in Windows, you have some data structures, okay. For example, E thread or K thread or TEB, which is thread environment block, okay. So you use these data structures to create thread related information, to get some information or to see what this thread is doing, update about the things related to each thread. So whenever you create a thread, you will have these data structures for each of the threads. So the E thread is the executive thread block, okay, which includes pointer to process to which threads belongs, and to K thread in the kernel space. So it is actually, this E thread is showing the relationship between the thread and the kernel thread and the process in which this thread is running, okay. The second thing is kernel thread block or K thread, and this is responsible for scheduling and synchronization information, okay. Kernel mode stack, pointer to thread environment block in the kernel space, okay. If these concepts seem difficult to you, then I would say that it's better that you please study the book. I told you before that it's nice, it's very helpful actually if you study the book chapters, the text of the book, and not just the slides, okay. Then the thread environment block, what it is just like the process control block, okay, because it contains a thread ID, the user mode state for the thread, and thread related local storage, and this is in the user space, okay. Any question? So you see there are three data structures in Windows, okay, E thread, K thread, and thread execution block, okay, TEB, and two of them, they are executing in the kernel space because it is related to the kernel thing. So all things related to the scheduling and synchronization or the kernel state, that is actually by the K thread, and also execution related things, which means for which process this thread belongs, the thread start address in the memory, a pointer to parent process, and other information related to the process of the thread, they are here in the P thread, the E thread. So this is a pointer to K thread, and in K thread there is a pointer to the thread execution block, which contains the actual things of the thread, okay. Just remember that we have kernel space and user space. So after Windows thread, this is the last slide of this chapter, which is about Linux threads, okay. Linux, in Linux, instead of threads, we use the term of task, okay. So actually a task is the same thing in Linux as we have threads in Windows operating system. So to create a thread, you use the clone system call, and clone will create actually a thread which will allow the child task to share the address space of the parent task or the parent process. And there are some flags. What is a flag? A flag means some properties which can actually control the behavior of the clone. If you change the property, it can be binary properties, okay. Flag is usually a binary property which can be true or false. So for example, the clone fs, okay, the clone file system, it means that if it is true, then the file system information will be shared. If it is false, then it will not be shared. Then clone VM is the virtual machine, virtual memory. Okay, so it says that if it is true, then the same memory space is shared. If it is false, then each of the thread will have its own memory space. Clone signal handlers, they are shared between the threads. Okay, and clone files, if you want to share the clone open files between different threads. Okay, so this was all about threads. Okay, and there is a structure which is called task struct, which points to the process data structures. Okay, we finished this chapter. Let me repeat very quickly what we have studied. Maybe before switching, I ask you people, what do you study? What did we study in these last 22 slides about thread?